Hi everyone. Today we're going to take a look at integration using completing the square and long division. So to start with, first I want to recap some old antiderivative rules that we know, right, for our inverse trig function. So example 1, integral of 1 over root 9 minus x squared dx, right? We should recognize the format here. This is going to be sine inverse of x over a. Here a is going to be 3. The next one, very similar, except this one is going to be secant inverse. And so remember the formula for that is 1 over a secant inverse of absolute value of x over a plus c. And again, a is going to be 3. And our last example where a is again 3, this one goes with tangent inverse. So this is 1 over a tangent inverse x over a plus c. So these three are good to keep in mind, especially for these techniques we're going to talk about today, specifically completing the square, more so than long division. Okay, so let's talk about our first completing the square example, example 4 here. So this is the integral of 1 over x squared plus 6x plus 10. And so how completing the square works is you group your x terms together, you take the coefficient of your linear x term, so in this case that would be the 6x here. I'm going to take the 6, right, and, oops, sorry, I changed colors there on accident. I'm going to take the 6, and the first step is always to divide it by 2. Now, keep that answer in mind from when you divide it by 2 because it's going to come into play later. So 6 over 2 is 3, but then I'm going to square that, and I'm going to get 9. So we took the coefficient of the linear term, right, divide it by 2 and square it. Now, I'm going to take this 9 and I'm going to add it into that parentheses, but if I'm going to add it there, I have to balance it out, and I'm going to subtract it from the 10. So let me show you what that looks like. We can go ahead and rewrite this integral as the integral of 1 over, and now we can write the quantity x squared plus 6x plus 9. So that's my perfect square trinomial there. And then I have the plus 10, but because I added 9, right, I'm going to have to subtract 9 here, right, in order to get this denominator to balance out. Because I can't just go around adding 9 into denominators. That's going to change the fraction, right? So that's why I have to go ahead and balance that out. And so the reason we do this is that this is a perfect square trinomial, like I said earlier, and if that doesn't sound like a familiar phrase to you, or it's just been a while, right, all it means is that you can factor it very nicely, right, and so this actually factors to x plus 3 times x plus 3, and that 3 comes from when we did 6 divided by 2, right, so I told you to remember that number, right, so I can go ahead and rewrite this as x plus 3 to the second power, and then 10 minus 9 is 1. Okay, so why would I want to rewrite my integral like this? Well, now, if I take a look at this integral, right, this lines up with the format of example 3. And so this is going to be a tangent inverse. Now, the main difference here is that in tangent inverse, we had just x squared. Here we have quantity x plus 3 squared. Now, some of you might be thinking, oh, so this is a composition now, right? I should do u sub. But the derivative of x plus 3 is 1, which is the same as the derivative of x. So I actually don't have to do anything different. I just have to go ahead and replace the x with x plus 3. And so here, right, I can say that a is going to be 1, right? And so this is going to be 1 over a, tangent inverse of x plus 3 over a plus c. Now, I don't need to leave all of this times 1 divided by 1, so let's just go ahead and rewrite it nicely. Tangent inverse of x plus 3 plus c. And feel free to use the arctan notation if you prefer that. Okay, so a lot of these completing the square questions are going to get you back to an inverse trig antiderivative rule. Okay, let's take a look at the next one. Example 5 here. This one's a little trickier. Okay, so first thing I notice in my square root is I don't like the way these terms are written. right? I'm actually going to go ahead and start off by rewriting them. So I'm going to go ahead and rewrite this as negative x squared plus 4x. And now, to complete the square, I could leave the negative x squared there, but it's actually better to go ahead and factor out a negative. So I'll leave it in the square root still, but it'll be negative quantity x squared minus 4x. Okay, and now inside of that parentheses, right, I have a linear term. It is negative 4, and that's what I'm going to use to complete the square. So negative 4 divided by 2 squared. So negative 4 divided by 2 is negative 2. Keep that in mind. That'll come back later. When I square that, I get 4. Okay, so now let's rewrite this. So I can rewrite this as the integral of 1 over the square root of, right? So this is going to be negative quantity x squared minus 4x plus 4. Okay, so I added a 4 in the parentheses, right? So I should subtract 4 outside of the parentheses? Not quite. Technically, I did not add 4 into the radical. I subtracted 4, right? Because I have this negative in front of that parentheses. So I actually, if you distribute, that's a minus 4. So to balance this out, I'm going to put a plus 4 on the outside. Sorry, I don't like those pluses. Let me redo that actually. Let's make that plus. There we go. That looks better. Okay, so I'm going to put a plus 4 here to balance out, again, what is technically a minus 4. And so I'm going to go ahead and rewrite this as 1 over the square root of, and I'm going to take this 4 at the end and actually move it to the front of my radical. This is going to be 4 minus the quantity, and then x squared minus 4x plus 4. That is all going to factor to x minus 2 squared, right? Which again is what I got from doing negative 4 divided by 2, right? That's always where you get that number. I mean, you could also just factor. You guys know how to factor, okay? And so now, what does this look like, right? This looks like the form of example 1, right? This looks like sine inverse, okay? And so this antiderivative is going to be, so this one does not have a 1 over a in front. It is just sine inverse or arcsine of x minus 2 over a, which is just 2 plus c. Okay. Okay, so example 6 looks a little bit trickier, okay, right? Because it's got this extra term. Pardon me. Now, a lot of people might look at this and go, oh, can I do some type of u substitution here, right? So let's just kind of game that out real quick. If I let u equal x squared minus 6, du would be quantity 2x minus 6 dx, right? Well, you could take this and go, well, I mean, I can divide everything by 2, right? I could go 1/2 du would be quantity x minus 3 dx, right? And so that matches up, doesn't it? I have x minus 3 dx. I have x minus 3 dx, right? Not quite. Because this x minus 3 is in the denominator. So technically, in the integral, this is dx divided by x minus 3. I need x minus 3 times dx. So u substitution does not work here, okay? And so, again, what I'm looking for here is trying to match it up with our rules where we get our inverse trig functions. And when I see something in front of a square root in the denominator, right, I know this is going to be a secant inverse. Okay, so let's see if we can make this match up and look nice. All right, so inside my square root, I have x squared minus 6x, right? I'm going to go ahead and, oops, let me unhighlight those. I'm going to take the linear term, so negative 6 divided by 2, square it. I'm going to get 9 again. Okay, and so let me go ahead and rewrite this integral as 1 over the quantity of x minus 3 root, big square root there. This is going to be x squared minus 6x plus 9. And then I had the plus 5. And so I'm going to subtract 9 from that to balance it out. Okay. Right? So add 9 minus 9 in order to get that to balance out. And so now I can go ahead and rewrite this. Let me space this out here a little bit. Sorry, folks, I crammed this in a bit too closely. This is going to be 1 over x minus 3 square root of, very conveniently, x minus 3 squared. And then 5 minus 9 is going to be minus 4. Okay, so for this one, right, what I really want with these secant inverse ones is what is being squared should match what is outside here, or sometimes there's absolute values here, right? But those things need to match, okay? And then a here is going to be 2. And so my answer for this one is going to be 1/2 secant inverse absolute value of x minus 3 over my a value of 2 plus c. Okay, so there's a few completing the square examples. Okay, now we're going to go ahead and switch gears here, and we're going to talk about long division. Okay, so find the antiderivative by first using long division. So let's look at the setup here. Integral of x squared over x minus 1 dx. So again, you want to try the techniques you know, right? One really common and bad mistake that students will sometimes make is they'll go x squared divided by x, and then x squared divided by -1. That's not how division works, right? You know, if I give you some numbers, let's just go off to the side here. If I have 8 over, let's say, 6 minus 3, right? That's not the same thing as 8/6 minus 8/3, right? That's not how we subtract with fractions, right? You need a common denominator, not a common numerator. So that definitely doesn't work, okay? Again, you can try u sub, right? You can pick the top or the bottom as the u, but it's not going to work out in your favor, okay? Really what you want to look for is look at the power of the numerator. It is larger or equal to sometimes the power in the denominator. That's how you know you're going to use long division. So let's go ahead and set this up. Okay, so we start off by making the house, right? And what is in the numerator, right, is called my, I'm having a blank here, dividend. Oh, this is embarrassing. I'll look it up later. X squared goes in the house. X minus 1, I know that's the divisor, so that's got to be the dividend. X minus 1 is going to go outside the house, okay? One thing I'm going to do right away is I'm going to put in my missing terms. I have 0 x's and I have 0 as a constant, okay? Okay, so now how does long division work? X times what, that which goes on top of the house, gives me x squared. Well, that's just going to be 1 more x, okay? So now I distribute. So I do x times x, so that is x squared. I do x times -1, so that's going to be minus x. And now the way I always do long division is I always subtract. Always. That's how I'm going to get these first terms to cancel out. It's x squared minus x squared. So those are going to cancel each other out. Okay, so that gives me nothing. And now 0 x's minus a negative x, so that's double x's or double negatives there. So that gives me a positive x. And then I have no constant to bring down, but I'll still write a plus 0 here. And now I do it again. X times what gives me x? Well, that's going to be a positive 1. Okay, and so now I distribute. 1 times x is x. 1 times -1 is -1. And now again, I subtract. So those x's cancel, right? And then 0 minus -1, double negatives, I get 1. And remember, the way you know you're done with long division, right, is when what is left is of a smaller degree than what you are dividing by. Okay, so this is how I know I'm done. And so now I can write my answer, right? So what is the result of actually doing this division? The quotient is x plus 1, but I have a remainder. So I can go ahead and rewrite this integral as my quotient, which was x plus 1, plus my remainder, which was just 1, over my divisor. Okay. Now, this is really nice because for these first two terms with your quotient, just straight up power rule, right? So we're going to get 1/2 x squared plus x. And now 1 over x minus 1, right? That one's not too bad, right? We should hopefully remember that that is natural log of absolute value of x minus 1. And then we, of course, throw a plus c at the end. Okay. So when the degree in the numerator, right, is greater, or again, sometimes even when it's equal to, right, you're going to have to do long division. Okay. And then you take your quotient plus remainder over divisor, and you can find the antiderivatives of those parts. Let's do another one. Example 2. Integral of 4x squared plus 5x minus 10 all over x plus 2 dx. So I already have my house set up, and now we start doing our long division. So x times what gives me 4x squared? That's going to be 4x. And so now I distribute that. And so 4x times x is 4x squared. 4x times 2 is 8x, positive 8x. But again, I always set it up. We are subtracting when we do long division. So 4x squareds cancel. And now what is 5x minus positive 8x? That is negative 3x. And I'll bring the negative 10 down. Okay. And now, same question, x times what gives me negative 3x? That's going to be negative 3. And so, oops, sorry, let me keep that up there, right? I'm going to distribute negative 3 into x plus 2. And so that's going to give me negative 3x minus 6. But again, I'm subtracting, right? I want negative 3x to cancel with itself, okay? So that's the only way I can do that is by subtracting them, all right? And now negative 10 minus negative 6, so double negatives, that's a plus 6 then. So negative 10 plus 6 is negative 4. That'll be my remainder, okay? So let's take the quotient and then our remainder, and we can rewrite our integral. So this is going to be 4x minus 3. And now you can write this a couple of ways. I like to write a plus, and then whatever my remainder is, I'll just throw in my numerator. You don't have to do it like this. If you'd rather just write minus 4, that's totally fine. But this is going to be over x plus 2. It's not going to affect your answer. You're going to get the same antiderivative no matter what. So a couple of power rules, 2x squared minus 3x, right? And then we're going to get minus 4 natural log absolute value of x plus 2. Oh, of course, we need a plus c. Okay. All right, and let's take a look at one last one. Example 3. This one, a little tricky. Feels like we should be able to factor and cancel some stuff, right? But x squared plus 9, sum of two squares do not factor, okay? Not with real numbers anyways. All right, so let's go ahead and set up the house. And actually, I don't really like how I did this. I wrote a plus 9 here, but I actually want to save some room for my missing term, which is 0x to the first. Okay, so I'll just put an extension over my house there. All right, so let's do this. X times what gives me x squared? That'll just be an x. So this is x squared plus 4x. Right, I'm going to go ahead and subtract. X squareds cancel. 0 minus 4x is negative 4x. And so I'll bring the plus 9 down. X times what is negative 4x? That'll be negative 4. And so now I'll distribute. I'll get negative 4x minus 16. Again, be careful. I am always subtracting to get them to cancel, right? Negative 4x minus itself cancels. 9 minus negative 16. Double negatives you actually add there. So your remainder is 25. That's a weird remainder. Okay, but it works. All right, so let's go ahead and rewrite this. So we get x minus 4 plus 25 over x plus 4 dx. And so we get 1/2 x squared minus 4x plus 25 natural log absolute value of x plus 4 plus c. Okay. Pardon me. Okay. So some of you might be looking at these last couple of examples and going, wow, these were extremely similar, right? Mantra, what do you have up your sleeve? How can you make this harder? Really, it's just the long division, right? If the polynomials have more terms, right, you really have to just be careful with all your algebra in these steps right here, because if you make any algebra mistake, right, whatever you end up with your quotient and remainder is wrong, and then your antiderivative is definitely wrong. So you really have to be sharp. Take your time with the long division, okay? Make sure you put in all your missing terms, right? That'll kind of help you organize your work here, okay? But yeah, that's all we have, all right? So a little bit of long division, right? And then a little bit of completing the square, combining with some inverse trig derivatives, okay? Or antiderivatives, excuse me. All right, and that's all we have for today. Okay, I'll see you guys next time.